Did you know that the secret behind high-performance engines can actually be traced back to Leonardo da Vinci? Centuries ago, he used nothing more than a wooden stick wrapped in sandpaper to smooth the inside of tubes. It was simple, manual, almost primitive. But here's the interesting part. The core idea hasn't changed. Today, that stick has evolved into one of the most precise internal finishing processes in modern manufacturing. If you've ever wondered how engineers make a hole perfectly round within just 2 microns, that's less than a fraction of a human hair, the answer is honing. So what exactly is honing? How does it actually work? And why is that cross-hatch pattern inside engine cylinders so important? Let's break it down step by step. What exactly is honing? Before we go deeper, let's clear up a common misunderstanding. Honing is not just sanding a hole smoother. It's a precision finishing process, a hybrid of grinding and drilling, designed to perfect both the size and the geometry of a hole. In most manufacturing chains, honing is the final sizing process. We're talking about tolerances in the range of 2 to 3 microns. And more importantly, honing controls 3 critical parameters at the same time: diameter, roundness, cylindricity. Many machining methods can control the diameter. Very few can truly correct geometric imperfections like ovality or taper, and that's where honing stands out. Now let's talk about something you've probably seen, the cross-hatch pattern. Because the honing tool rotates while moving up and down, a motion called reciprocation, it creates that signature X pattern on the surface. But that pattern isn't decorative, it serves a function. Those microscopic grooves act as reservoirs for oil and lubricant. Without them, moving parts, especially in high-temperature environments like engines, would suffer from excessive friction. In extreme cases, components could seize or weld together. That's why honing is often described as the fine-tuning stage of manufacturing. It's not just finishing, it's performance optimization. Now that we understand what honing is, let's look at how it actually works. The process can be broken down into 3 clear steps. Step 1, setup. First, the workpiece is securely clamped. Then the honing tool, called a hone, is mounted. This tool contains abrasive stones, often made of diamond or CBN, designed for controlled material removal. Step 2, expansion. Once the tool enters the hole, the stones expand outward radially. They press firmly against the internal wall, sometimes with pressures reaching 2,500 kPa. But this isn't brute force cutting, it's controlled correction. The goal here is to gently remove high spots and restore perfect geometry. Step 3, movement. Now comes the synchronized motion. The tool rotates, it reciprocates up and down, and coolant continuously flows to prevent overheating. There are 4 critical parameters to keep in mind during the honing process: abrasive selection, spindle speed, stroking speed, and honing pressure. If you want to remove material faster, pick a coarse grit, increase the spindle RPM a bit, stroke a little faster, and apply more pressure, but carefully, as too much can damage the surface. If you want a smoother mirror-like finish, do the opposite. Use a finer grit, lower the spindle speed slightly, control the stroking speed, and use moderate pressure. It's all about finding the right balance between speed, motion, and pressure. So, how do engineers decide when honing is truly necessary? There's a simple rule of thumb. Is this hole functional, or is it just for assembly? If the hole is simply there to hold a bolt, honing may not be required. But when a hole must maintain extremely high roundness, withstand long-term wear, and meet strict lubrication or sealing requirements, honing becomes almost mandatory. Let's break that down further. First, geometric accuracy. Honing excels at correcting oval or tapered holes left behind by previous processes. Second, functional surface. That cross-hatch pattern we talked about is critical in engine blocks, gears, and hydraulic systems. Third, dimensional stability over time. Honed surfaces maintain performance under long-term mechanical stress. In industries like the automotive industry, honing is essential for engine cylinders, and in aerospace and medical applications, where friction, sealing, and precision are mission-critical. To really understand honing's role versus other finishing processes, a precision hole typically evolves like this: drilling, boring, internal grinding, honing, lapping, or polishing. Each step improves accuracy. If your only target is diameter size, boring or grinding can achieve that. But if your goal is performance, meaning lifespan, lubrication efficiency, and sealing reliability, honing is the process that delivers. Here's the key takeaway. Honing is not about making a hole shiny. It's about correcting geometry, creating a functional surface, unlocking long-term performance. If you're looking for a reliable manufacturing partner for honing machining, RapidDirect offers one-stop manufacturing solutions designed around your budget and application needs. If you found this breakdown helpful, don't forget to like, comment, and subscribe. We'll continue bringing you deeper insights into manufacturing, materials science, and real-world engineering.